Hello! In this video lecture I want to talk about the Bloch equation in magnetic resonance. They are used to describe nuclear or electron spin magnetization of a rather simple spin system, such as, for example, isolated spin 1/2 particles. Basically, Bloch equations are introduced to account for relaxation processes accompanying spin magnetization precession in external magnetic fields. Okay, let us consider a way how the Bloch equations can be introduced semi-empirically. As I told in my other video lectures, or how it can be found in literature, the motion of magnetic moment in magnetic field can be described conveniently in a rotating frame. It means I have a laboratory frame x, y, z and a frame x prime, y prime, z prime rotating with the angular velocity omega. The z and the z prime axes are parallel. In the rotating frame, the motion of a magnetic moment m is determined by the equation where the time derivative of the magnetic vector m is determined by a vector product as written here. Now I define the magnetic field B in the laboratory frame. It has two components. The first component oriented along the x-axis and oscillates with the frequency omega, and the second component is oriented along the z-axis, is constant and has a magnitude b0. The component on the y-axis is equal to 0. As we know, the oscillating magnetic field along the x-axis can be presented as two magnetic fields of half magnitude rotating in opposite direction with the angular velocity omega. With this magnetic field, the equation for the motion of magnetic moment in the rotating frame can be written in the following form. Here the cross product is expressed via the determinant, and the value of magnetic field is taken in the rotating frame. Furthermore, I will introduce the following variable. Omega 0 is equal to minus gamma b0, delta omega is the difference between omega and omega 0, and the variable omega 1 is equal to minus gamma b1 divided by 2. With these notations, the last equation can be written in a little bit shorter form. Now, by computing the determinant explicitly, I can determine the rate of change for each component of the magnetization vector. Here I have dmx over dt is equal to my multiplied by delta omega. dmy divided by dt is equal to minus mx delta omega minus omega 1 mz, and dmz over dt is equal to omega 1 my. In these equations, the time changes of the components mx, my, and mz have such characters that they lead to a rotational motion. However, in reality, the magnetization vector is not just rotating. There are processes which cause its decay and return to the equilibrium value. Therefore, I will add additional term to the expressions which determine the rate of changes of magnetization vector components. For example, the component mx is not just increased by the component my multiplied by delta omega, as it is written in the first equation, but also it is reduced by itself. The larger mx is, the stronger it is reduced, characterized by the relaxation time T2. Therefore, I will subtract mx divided by T2 from the first equation. The component my is treated in the similar way. It is also decaying with the characteristic time T2. However, the component mz is not decaying to zero. It returns to its equilibrium value, m0, and it returns with its characteristical time T1, which is in general different from the relaxation time T2. In order to describe this process, the term mz minus m0 divided by T1 is subtracted from the last equation. In this way, I have obtained a system of three equations for three components of the sample spin magnetization which processes in the presence of relaxation processes. It is convenient to present this system of three differential equations in a matrix form. Sometimes this form is helpful for further interpretation of the spin magnetization behavior. Okay, let us talk now about the solution of the Bloch equations. Remarkably, it is possible to determine general solution for the vector m as a function of time. However, it will be described by quite large formulas. Interestingly, our Bloch equation can be easily solved for some special cases which are experimentally relevant. In the first such case, I will assume that B1 is very small and the longitudinal magnetization mz is almost equal to the equilibrium value m0. In this case, the first two Bloch equations will contain just two unknown variables mx and my. Since the variable mz which enters the second equation will be substituted with the equilibrium magnetization value m0. Hence, I can write the following two equations for the variables mx and my. Furthermore, I will consider the case when the magnetization becomes stationary. In other words, after a long time when the relaxation processes balance B1 irradiation. In this case, the time derivatives of mx and my are equal to 0. That means that mx and my have reached their stationary values. Hence, I obtain two simple linear equations. This gives us immediately the expressions for my and mx. Which look like Lorentz curve as functions of parameter delta omega. Now I can plot my as function of delta omega. This is a Lorentz curve, the width of which is determined by the inverse value of the T2 relaxation time. The curve mx is obtained from the curve my by the multiplication by delta omega t2. Since mx and my are observable experimentally, in some cases the obtained curve mx and my can be used for analysis and interpretation of measured spectra, which record value of transversal magnetization component mx and my as function of the frequency offset delta omega. Okay, now I want to consider another partial solution of the Bloch equations, which is a little bit more general than this which I have shown above. Here I will not make the assumptions that the time derivatives of the magnetization vector components mx and my are equal to 0. Experimentally, it means that we do not take long time to measure magnetization at some spectral position delta omega, or we do not wait for long time until relaxation processes balance the effect of irradiation on the spin system. Such approach is called rapid scan because the frequency is changed very fast during the record of the spectrum. Okay, let's go back to the system of two equations for the magnetic moment components mx and my, which have been written already above. Please note that dmx over dt and dmy over dt are not equal to 0 in this case. It is convenient to introduce a new function m, small m, which is a sum of capital Mx plus I complex unit multiplied by My. With this, I can write one complex equation which corresponds to the system of two equations for Mx and My. I have dm over dt is equal to minus m divided by t2 minus I delta omega m minus I omega 1 m0. It is clear if we take the real part of this equation, we'll obtain the first Bloch equation, and if we take the imaginary part of this equation, we'll obtain the second Bloch equation. Hence, I have obtained a linear differential equation of the first order, which is inhomogeneous. It also includes the parameters T2, delta omega, and omega 1. It is important to note that the parameter delta omega is time dependent. Here, I will consider the case when the frequency offset delta omega is changed linearly with the time. It means that the time derivative d delta omega over dt is constant, and I will denote it with the letter b. Since the time t and the frequency offset delta omega are linked with a linear relation, I can say that the function m of t is equal to some function g, which depends on the frequency offset delta omega. With this, I can express dm over dt using basic rules of calculus. Hence, I can rewrite this equation in terms of the function g and variable delta omega. Please note, I have obtained a linear differential equation of the first order, which is inhomogeneous. It also has constant and variable coefficients. The solution of this equation is known, and the procedure how to obtain it is written in mathematical textbook. Just to explain it quickly, I'll write a partial solution and will demonstrate that this partial solution satisfies our equation. The solution is g of delta omega is equal to minus I omega 1 m0 multiplied by an integral of an exponential function, where f of tau is equal to IB tau squared divided by 2 minus tau divided by t2 minus I delta omega tau. In order to check whether this is a solution, I will calculate the left side of this equation and will check whether it coincides with the right side of this equation. Okay, the left side of this equation can be calculated using the last formulas, which give us the following after the derivation with respect to delta omega. Here we have an integral which is very similar to those which defines the function g of delta omega, with the only difference that it contains additional tau. Now I will rearrange this integral a little bit, and also I will subtract the terms 1 over t2 and I delta omega, and immediately I will add this term. At the end, I will just change the shape of this integral, but not the content. The purpose of this rearrangement is to organize a tau derivative of e to the power of f of tau. And we see that the product of IB tau minus 1 over t2 minus I delta omega multiplied by e to the power of f of tau is equal to the tau derivative of e to the power of f of tau. Now, using this expression, I can rewrite the last integral in the following form. It has two terms. The first can be easily calculated because this is the integral of a derivative, and the second one is rearranged slightly. As it can be seen easily, the first term is equal to minus 1, and the second term is very similar to the definition of the function g of delta omega. With this, I can write that pg derivative with respect to delta omega is equal to minus 1 over t2 minus I delta omega multiplied by g minus I omega 1 m0. Now I can compare the obtained result with the right side of our initial equation, and I see that they both are equal. With this, I have demonstrated that the function defined by these formulas is a solution of Bloch equation for the case of rapid scan. Explicitly, the function g of delta omega is written in this form. Let me make few comments regarding the properties of this function. First of all, let us consider the situation when the scan rate b is equal to 0. In this case, the function g of delta omega is simplified. Now, the argument of the exponential function under the integral contains only the linear terms. This allows me to calculate the last integral analytically. It is well known that this integral in the limit from 0 to infinity is equal to 1 over T2 plus I delta omega. As we see, the result is a complex value which has real and imaginary parts. Let me write them separately. The real part is proportional to delta omega T2 divided by 1 plus delta omega T2 squared. And the imaginary part has a Lorentzian form with respect to the variable delta omega. Now, if I compare the real and the imaginary parts of g of delta omega to the expression for mx and my which I have obtained in the stationary case, that is when the time derivative of mx and my were assumed equal to 0, then I will see that these results are equal. For a better understanding of the function g of delta omega, let us plot its real and imaginary parts. Here I will take a spin system with the T2 relaxation time equal to 200 nanoseconds. Also, I will take a rather slow scan rate B equal to 2 pi terahertz per second. Later, it will become clear why this scan rate is considered to be slow. With this, I obtain the blue curve for the imaginary part of g of delta omega and the brown curve for the real part of g of delta omega. As we see with these values of the parameters T2 and B, the obtained curve look very similar to the curves mx and my which were obtained in the case of stationary solution. Now let us increase the scan rate p by the factor of 10. B is now equal to 2 pi multiplied by 10 terahertz per second. The plots for this value of p are shown in this figure. As we see, the real and the imaginary part of g of delta omega start wiggling. That is a clear indication of rapid scan effects.
Generally, it can be shown that the rapid scan effects appears if the scan rate, b, becomes larger than 1 over T2 squared. Let us verify this with our data. In our case, 1 divided by T2 squared is equal to 25 terahertz per second. In the second case, the scan rate, b, is equal to approximately 62.8 terahertz per second, which is larger than 1 over T2 squared. In the first case, when almost no rapid scan effects are observed, the scan rate, b, is 10 times smaller than in the second case, and also it is smaller than 1 over T2 squared. Well, now I would like to summarize the results presented in this video lecture. In the first step, the Bloch equations, which account for the relaxation of magnetic moment precession, were introduced. In the second step, these equations were solved in two cases. First, it was assumed that a low irradiation power is applied for a long time, without causing significant reduction of the longitudinal magnetization vector component, mz. Under such conditions, the stationary values of mx and my were determined as function of the frequency offset, delta omega. In the second case, the solution of the Bloch equations was found again under assumption that the longitudinal magnetization, mz, remains almost unchanged, but the stationary state requirement was skipped. Such situation corresponds to the rapid scan regime of spectral recording. Generally, the Bloch equations can be solved for other interesting situations. For example, when B1 field is not small, leading to a large deviation of the initial equilibrium magnetization. Or, when we are interested in exact time dependence of the magnetization vector for a fixed frequency offset, delta omega, and relaxation times T1 and T2. However, the analysis of such solutions goes beyond the scope of this lecture. With this, I would like to finish and thank you for watching. Bye bye.